The objective of this lab was to estimate the mass of the black hole by analyzing the motion of the star, and the method through which I went about doing this was using the CSV file that we were given to kind of predict what the star's motion was, and then use Python to find the net force on the star for all the points in the data set to ultimately figure out the mass of the black hole. Some of the principles that we used in this lab was the momentum principle. So we have that the final momentum is equal to the initial momentum plus F net over delta t. And then we also know that F net is equal to delta p over delta t. And in this case, we actually had to use F net in the parallel direction and F net in the perpendicular direction. And so the formulas for that are shown below. And then we also use Newton's law of universal gravitation. And so the force of gravitation is equal to negative g, which is a constant, times the first mass over the times the second mass over the magnitude of r squared times r hat. And this is all shown in the code. So we made a lot of changes to the code. First, we had to change our email address, so I did that. And then we had to change, we had to change the mass of the star, which was given to us. It was 2 times 10 to the 30th. We also changed delta t. And then starting over here, we started making a lot of changes. So first, I had to change the way in which we calculated the initial and final momentum. So that would be the star's mass times v initial and v final for momentum, initial and final. And then to calculate delta v and delta p, obviously you have to do the difference between the final velocity and initial velocity and final momentum and initial momentum. And then over here is where we calculated dp over dt, which is the rate of change in momentum. So that's the change in p over the change in t. And then which is shown over here, and then F net is equal to mass times acceleration, which is the same as the mass times the rate of change of velocity, which is also equal to the rate of change of momentum. And so you can see that in the code as well. And then I calculated p hat, which is equal to the initial p, initial momentum over the magnitude of the initial momentum. And then in order to find the magnitude of dp over dt, we have to do the difference in magnitude of the final velocity and initial, or not final momentum and initial momentum, over delta t. So that would be the magnitude of the rate of change. And then we had to divide that up into trying to find the F net for parallel and perpendicular, which I did over here. So for the parallel, I did the magnitude of dp over dt over delta t to find, that's shown over here. And then for perpendicular, that would just be the difference between the overall dp over dt and the parallel dp over dt, which is shown because we calculated the difference. And then F net would just be equal to the perpendicular dp over dt. And then this is all the same. We had to change the arrow scale, and then over here we had to multiply all the forces times the arrow scale as well. And then in the end, we just printed out all the values. And so my final value for the mass was 3.58 times 10 to the 31st kilograms. And I noticed that the arrow would grow larger along with an increase in magnitude of F net. So the magnitude of the net force was greatest when the star was closest to the black hole. And to answer the concluding questions, what does it mean, and like what the difference is between calculated the parallel and perpendicular force versus the overall net force, was that for the overall net force, we had to do the F net parallel plus the F net perpendicular, and it only affects the star's motion. Whereas when we were calculating the parallel and perpendicular net forces, it would only show kind of how the star is moving and wouldn't affect the motion itself. And then you could see, like, within the code, we had to do a lot more calculations to find the parallel and perpendicular forces. And in this case, the dp over dt, as in like the parallel and perpendicular forces, had to be found first for this problem, and then related to the F net. And no, it's not really possible to tell the difference, because if the motion of the stars is the same, then the data points would essentially be the same too. So the force of gravity would not be affected, since we're using the same values as above. So you would not be able to tell a difference in that case. Yeah, that's it.